Okay, so for this lecture, we're going to introduce the next fundamental concept in calculus. So, and by that I mean we're going to start talking about integrals. So, in order to understand integration or integrals, we need to know about what are called antiderivatives. So antiderivatives and indefinite integration. Okay. So let's begin with the definition. So a function, capital F, is an antiderivative of little f on an integral I when f prime of x is equal to f of x for all x contained in that interval. So antiderivative. Okay. So for example, consider the function f of x equals to 3x squared. Okay. So can we find an antiderivative of this function? In other words, can we find a function whose derivative is equal to f? So think of a function whose derivative would be equal to that function. Any guesses?
X cubed.
Right, so that would be one, right? So one possible guess would be f of x equals to x cubed. And that's because if we take the derivative with respect to x of this function, we have 3x squared, which is equal to f of x. So the derivative everywhere of that function would be equal to that function. Any other guesses? In other words, there can be more than one.
X cubed plus some other number, really any.
Right, exactly. That's more general than I was expecting, but that's exactly the case. So where c is just a constant. Right, because when you take the derivative now, right, if that's a constant, then you're still going to get the function 3x squared, right? So when considering the problem of finding antiderivatives, you don't have just one function, you have infinitely many functions, right? So like when looking at the antiderivative of this function, one of them is x cubed, which looks like that, right? That's one antiderivative of that function. Another one would be x cubed plus 1, right? Another one would be x cubed minus 1. So forth and so on. Each one of these functions is a valid antiderivative of that little f. Okay? So, okay, that's something, right? Now, what's nice about this is that antiderivatives can describe a lot of things, in particular fields. So like for example, like electromagnetic fields, the collection of antiderivatives forms, you can imagine like this is like somehow a field that something would be flowing through, right? In the study of finding those antiderivatives, I'll just go ahead and say, so the study of solving equations for antiderivatives is called differential equations. Which maybe some of you have heard of, right? So for example, y prime equals to 3x squared is a differential equation. Since in this equation, you would be asked to solve for y. Right, like this is an equation of y prime, the derivative of y. What is y, right? So a lot of times when dealing with these types of problems in particular, you have a whole infinite collection of possible antiderivatives, but to narrow down the possibilities for the solutions to this differential equation, you'll have what's known as a initial condition. So, for example, you might encounter in a differential equation type class, you might encounter the following problem: solve y prime equals to 3x squared, where say 0, 0 is an initial condition. Right, so you have all of these possible solutions for this differential equation, but the only one that satisfies this initial condition is y equals to x cubed. Since 0 is equal to 0 cubed is satisfied, and all the other ones wouldn't work. For example, like if y was equal to x cubed plus 1, then when x is equal to 0, y is equal to 1. Which means that this solution to the differential equation wouldn't satisfy this condition. Okay. So the whole field differential equations actually, it's not just a topic that I'm vaguely mentioning in this lecture. Differential equations is its own field. People will get their PhDs in differential equations. There's entire textbooks written on differential equations. And it's one of the most applied subjects in all of mathematics from the standpoint of physics and engineering, even problems in data science. And learning how to solve differential equations is incredibly important to so many different areas outside of mathematics. In fact, I encourage all of you that have a inclination towards mathematics as data science majors to actually take a course in differential equations, just so that you see at least ordinary differential equations once. And I'll try to sprinkle in as much as I can in this course or in our following lectures about differential equations, but it really is a very very interesting field of mathematics, of applied mathematics. Okay, but in a sense, we will be doing some type of differential equation type stuff, because from the next few weeks, we're going to be looking at finding antiderivatives. And antiderivatives are simply solutions to equations where the variables are derivatives of functions. Okay. So let's maybe look at some examples of finding antiderivatives in terms of what we will call indefinite integrals. Okay, so what is an indefinite integral? So an indefinite integral looks like this. So we have this like elongated sum symbol of f of x dx, and this is defined as the antiderivative of f with respect to x plus some constant. So that's what the indefinite integral looks like, and the integral symbol is this elongated s, which in later lectures we'll learn was meant to emphasize something about a sum. Okay, so what are the components here? Well, this is an indefinite integral. This is called your integrand. This tells you with what variable you're taking the integral with respect to. So this is called the variable of integration. This is simply the antiderivative of f. And then this c here, as we mentioned before, it's just a constant, and this is called the constant of integration. So those are the components of the indefinite integral. Okay. Okay, so there is a table of properties of integrals in your textbook that I encourage you just to like take a picture of or write down those formulas and just have them next to you whenever you need to use them. For example, the table will contain things like the integral of c, or the indefinite integral of c times f of x dx is just equal to that c times the indefinite integral. This is where c is a constant. Or I'll call it k to not confuse you with that c. And so you can take constants out of the indefinite integral. You have the indefinite integral of, say, the sum of two functions. Then this is the sum or difference of the indefinite integrals. Plus or minus respectively. Okay. And a few others, right? And again, I encourage you to go and look at that table and just kind of write it down. I'm not going to spend 15 minutes writing down every single property, but basically it's just a collection of properties that we'll use when evaluating these indefinite integrals. So, for example, maybe we can just like show an application, like maybe that property. So if we wanted to look at this indefinite integral here, then we have a constant there that we can take out. And then the problem reduces just to finding what the antiderivative of x squared is, which is what? What's the antiderivative of x squared? What function whose derivative gives you x squared?
One-third x cubed.
Right, right. But don't forget the constant out there. And then we have our constant of integration. So that would be the answer to that indefinite integral. All right, so let's do another one. Maybe I'll do it on this board here. So maybe say we want the indefinite integral of 3x to the power of 4 minus 5x squared plus x, all with respect to the variable x. Okay. So, okay, we're just going to apply these two rules over and over. So this will be like 3 times this indefinite integral minus 5 times this indefinite integral plus this indefinite integral. Right, I just like split the sums and differences, and then that took out the constants that are multiplying our basic functions. So what's the antiderivative of 4? I mean, x to the power of 4.
One-fifth x to the fifth.
Right, 1/5 of x to the power of 5 plus some constant. Right, so this will be 3 times 1/5 x to the power 5. And then I didn't do it here. I kind of skipped a step, but I'll do it here. Plus some constant C1. So that's like the answer to this indefinite integral is 3 times all that business. minus 5 times the antiderivative of x squared, which is 1/3 x cubed plus some other constant, maybe c2. And then the antiderivative of this is just 1/2 x squared plus some other constant, maybe c3. Okay, so now we just kind of simplify this out. So this is 3/5 of x to the power 5 plus 5 times c1 minus 5/3 x to the power 3 minus 5 times c2 1/2 x squared plus c3, and then we're done. So 3/5 of x to the power 5 minus 5/3 x to the power 3 plus 1/2 x squared plus c, where c is just equal to 5 times c1. Oh no, not 5, 3 times c1. Minus 5 times c2 plus c3. And when you're writing the solutions, you typically won't do that. I'm just writing it so that you see it. That's a constant, that's a constant, that's a constant. So just put them together. That's the constant at the end. So then this would be the answer. Okay. All right, so let's just look at another example. Say indefinite integral of x plus 1 all over root x dx. Now that, I wouldn't be able to guess it, but that looks way too complicated to find the antiderivative of. When you get something that looks something like that, right, what you should probably do first is simplify and expand the expression as much as you can into little pieces. So for example, this is the same thing as saying that, right? Same thing. So then what does this become? Like that, right? If I just use my rules for exponents. But then now I have a sum of the functions, and I can just group them together. Wait, make sure about something real fast. Oh, yeah, fine. So now we've taken that kind of complicated looking function and we split it into little pieces, and now we can more or less guess what the answers are, right? So right here, what's the antiderivative of x to the power 1/2? How would you find that? So without referring to that table in your book, let's just see if you can think about this. So what do we know about derivatives of these things, right? So right? Okay. So this is like your f of x in there. Here's like your little x in there, right? So we can go from here to there. Can we go from here to there? Right, like if, for example, we have this is what we want. How did we do it before, right? When we had so whose derivative gives you that function there? I heard one of you say it earlier. Right? Whose derivative gives you x to the power 4, for example?
1/5 x to the 5th.
Right. So what do you think goes inside of here?
One
Um,
over. Go ahead.
Oh, sorry. 1 over n plus 1 to the n plus 1. Or times x to the n plus 1.
Yeah. Now, the only caveat I have to say about this, though, and we'll talk about this more next lecture, is that in order to use this, n cannot equal -1. That has to wait. But for all other values of n, this will work. Okay. So here with this piece now, we have, this is like our n, right? So we have to add 1 to that. So it'd be 3/2, right? So it'll be 1 over 3/2 times x to the power 3/2. Or in other words, 2/3 x to the power 3/2 plus some constant c1. And here we have to add 1 to that, which is just like a half. So then 1 divided by a half is 2 times x to the power 1/2 plus some other constant c2, and then you're done. And the nice thing about finding these indefinite integrals is that you can check yourself, right? Like if you take the derivative of this, you better get back that, or that, and you will. Okay? In particular, maybe I should make note of that you can check yourself. If you take the derivative of the indefinite integral of x dx, whatever that happens to be, it better equal f of x. It better. Right? So this is equal to that, right? So but we claim to have found that, right? So that's like the derivative of what we found. This. So let's go ahead and double check ourselves. So derivative here, 3/2 times 1/2 is just 1, and then 3/2 minus 1 is 1/2, right? So this piece here will have a derivative of x to the power 1/2. 1/2 times 2 is just 1, and then 1/2 minus 1 is negative 1/2. Derivative with respect to x of a constant is just 0. So this is equal to root x plus 1 over root x. And if you combine like terms, you get x plus 1 all over root x. And we see that's my little f right there. And then here it is again. So you can think of integration and differentiation as like inverses of each other. You take the derivative of an integral, it's like you're like canceling out the integral, and you're left with just the original function. Right? By the way that everything has been defined in terms of antiderivatives. Okay. So from this section, the suggested problems are 15 through 43 odd, and then 56. Okay. All right, so I'm going to go ahead and stop the recording here.